Hello, this is Professor Kuehn. We've been talking about Newton's Principia, Book 1, Section 2, Proposition 4, or Theorem 4. In the last lecture, we focused on the corollaries. Remember, the idea is that if we have two objects in circular orbits, the larger circle has a radius capital R, the object is moving at a constant speed capital V, and it takes a time capital T to go all the way around. The smaller circle has a radius little r, it's moving at a constant speed little v, and it takes a time little t to go all the way around. Then we can deduce a relationship between the forces, the centripetal forces required to hold them in these orbits, and those are given by Corollary 1, for example, which relates the centripetal forces to the orbital speeds and the radii. Oops, and I have a mistake here, v squared over r. Corollary 2, we've just changed variables, and now we're writing the centripetal forces in terms of the orbital radii and the periods of the orbits. Corollary 6 is a little bit different. It's claiming that if we were to measure, so given these formulas, if we were to measure the relationship between the periods and we were to happen to find that they go as the ratio of the radii to the 3/2, or the sesquialteral ratio, as he would say, then we can make a conclusion about the relationship between the forces. They should be 1 over r squared kind of forces. This, by the way, is going to be a very important conclusion that Newton is going to rely on. Why is that? Well, because this is a heads up. So later on, he's going to say, if we look at the planets, for example, Venus, or Saturn, or Mars, and we look at how long it takes them to get around the sun, the periods of their orbits, it just so happens that the periods of their orbits are related to the orbital radii to the 3/2 power. So if, for example, you compare the time of orbit of Jupiter to the time of orbit of Saturn, and you compare the radius of orbit of Jupiter to the radius of orbit of Saturn, they obey this relationship. That, by the way, is called Kepler's third law. Newton didn't discover this. It was Kepler, Johannes Kepler, who discovered this. This is Kepler's third law of planetary motion, not to be confused with Newton's 3 laws of motion. This is Kepler's third law of planetary motion. And so if that's the case, which it is for Jupiter and Saturn, or comparing Jupiter and Mars, or Mars and Saturn, or Venus and Mars, any two planets, then we can conclude that whatever force is holding them in orbit, it must be a 1 over r squared kind of force. So this is going to lead him to the idea that whatever force is holding them in orbit, it must have the form of 1 over the radius of orbit squared, an inverse square law force. This is going to be really important later on. It's going to shape Newton's universal law of gravity. Okay, so let's now talk about Corollary 9. This one is, once again, a little bit different. And what this corollary is claiming, I'm going to draw a picture first, then I'll write down what his claim is, and I'll explain it. So if you are looking at an orbiting object, so we're not comparing two orbits. In this one, we're going to compare the distance moved by an orbiting object. So think for a moment, think ahead, to the moon orbiting the Earth. So this might be the moon out here, and that's exactly what Newton has in mind, by the way. So we've got the moon out here orbiting the Earth. So this would be the Earth at the center. And then think about another object that instead of orbiting the Earth is simply falling straight toward the Earth. Okay, so this is the orbiting object. And this is the falling object. Okay, and I'm going to label these points A and F. That'll be this point right there. And we'll call this point right here L. And we'll call this point S. And I'm going to call this point right here D. And let me draw a few lines here. This will be suggestive. These are going to be important lines later on. Okay. Now, what is Newton's claim in Corollary 9? He is going to say that there's a relationship between the distance an object orbits and the distance the same object would fall if you were to suddenly stop its orbit and let the centripetal force that had been holding it in orbit simply make it accelerate downward. Okay, so this is the classic experiment where we're comparing the orbit of the moon to the falling of an apple, for example. Okay, so here's the claim, is that the arc that is traversed by an object, like the moon, orbiting a central point, although it doesn't have to be the moon, central point S, due to a centripetal force during a given time interval. We'll call this delta t. So this, think about this right here. That is the arc traversed by the object orbiting the central point S during some time interval delta t. Now, what is that arc? It's going to be related mathematically to some other quantities. So he says that arc is a mean proportion. I'll explain what I mean by that in a moment. A mean proportion of two quantities. I'll just write this out and then I'll explain it for you, of two quantities. And those two quantities are, first, the diameter of the orbit, and that would be, in our case, AD, the line segment AD, and the other quantity is the distance it would have fallen. It would have fallen during the same time interval due to the same force. Okay, so in order to understand this claim, we're going to have to understand a few terms. So first of all, what is a mean proportion? So what is a mean? We're going to have to understand mean proportion, and we're going to have to understand what we mean by these two quantities. So what is a mean proportion? You may recall this from your earlier mathematics classes, but I'll just remind you. So we would say X is a mean proportion of quantities little d and big D if D is to X in the same ratio as X is to capital D. So we would say then X is a mean proportion of little d and big D. So this is a little aside, okay? That's what we mean by a mean proportion. So now what is he claiming here? He's saying the arc that's traveled, let me get some orange up here. So the arc that's traveled during this time interval, that length right there, is a mean proportion of the orbital diameter, that would be this right here, and the other quantity is the distance it would have fallen during the same time interval due to the same force. So let's make that blue. So that would be this. I don't like that color. Let me go back. Let's make it green. That's the distance it would have fallen during the same time interval. In other words, what he's claiming is that arc length is a mean proportion. So let me color code this to make it more obvious. So AF, that arc length, is a mean proportion. So I'm going to write it like this, like the X over here. It's a mean proportion of the diameter of the orbit and the distance it would have fallen. Okay, so I'm just going to write, you can put these in either order. So let's go ahead and do this. So the distance it would have fallen, we'll put that run right here. And the diameter of the orbit, AD. So this is what he is claiming here. AF, that arc length, is a mean proportion of the distance it would have fallen. So if, for example, you have this orbiting object, it's feeling a centripetal force to stay in orbit. Suddenly God puts out his hand and stops the orbit. It's still feeling a force that's trying to pull it in. So as a result of that force, it's going to start falling straight down. So if you let it fall for some time delta t, that's the same as it would have gone over to here, that distance AL is the distance it would have fallen. Okay, so that arc length AF is a mean proportion of AL and the diameter of the orbit AD. That is the claim, okay, that he's making. So that is Corollary 9. Why is Newton interested in this? Before I explain how one arrives at this, let me explain why he's interested, okay? What Newton is interested in is doing, so why is this important? Newton is going to want to say that it is the same force that causes the moon to orbit the Earth and that makes apples fall from trees. So Newton is going to claim that the exact same force, the same, and he's going to say it's the gravitational force that causes the moon to stay in its orbit Newton's going to claim that the same force that caused the moon to stay in its orbit also causes apples and other things, apples, to fall from trees. Okay, and keep in mind that we take this for granted. Well, yeah, of course, it's gravity that causes apples to fall. It's gravity that keeps the moon in orbit. That's really not obvious at all. They seem to be two totally different things. If you hadn't been indoctrinated, so to speak, since you were little, to think that they were the same force, how would you arrive at this conclusion? What Newton is doing is he's trying to provide a mathematical analysis and a reason for why one should think that there's a force that's pulling on the moon and a force that's pulling on the apple, and those have the exact same cause. Okay, and so that's what he's aiming at here. He has to make the case. It's not enough to simply assert that that is the case. I am not going to go through this proof in detail. What I am going to do is give a motivation for when this is a small arc length and a small distance traveled, one can arrive at this relationship. And it's really related to the same proof we used earlier. If you draw a diameter of a circle and you have an arc length like this, and then you draw a line straight over like this, and then you connect these by a chord, and then you draw two more like that, and we will call this A right here, and we'll draw a straight line over there to E, straight line down there. We'll call this point B. We'll call this point C and S and D. You might recall that for very small time intervals, the arc length can be approximated by this chord length right there. They're approximately the same quantity. And furthermore, you might recall that this triangle ABC, was similar to triangle ABD. And because of that, so ABD, and because of that, that implied that AC is to AB in the same ratio as AB is to AD. Right? Because those two triangles were similar triangles, so the short side of the little triangle is to its hypotenuse in the same ratio as the short side of the big triangle is to its hypotenuse. And that formula right there looks an awful lot like this formula right there, relating the distance of fall and the diameter of the orbit and the arc length of the orbit. Okay, so that is the way that he is going to go about demonstrating this relationship. Okay, now when you do this in lab, what you're going to have to do is you're going to have an orbiting object, and you're going to know the force that's holding it in orbit, and you're going to be able to measure the distance it moves in a given amount of time, and you're also using the force, you're going to be able to figure out the distance that it would move inward if you were to stop its orbit. And then you're going to try to determine if Corollary 9 in fact holds for your orbiting object. So we'll come back to this later when we do the force and rotation lab. Otherwise, I will leave this as it is for now.